Okay, so let's start. So today we will finish our review of some fundamental properties of analytic geometry. We are interested only on those parts which we will use with the partial derivatives and integration. So let's review what we did. Okay, so we considered vectors in R3. So if we had two vectors P, let's say P1, P2, P3, and say Q, Q1, Q2, Q3, we recall that their addition or the difference between them is pointwise, P1 plus or minus Q1, P2 plus or minus Q2, P3 plus or minus Q3. So these are vectors in R3. Of course, the next thing is how do we multiply these? So we have two products we mentioned last time. We have dot product. Okay, so we consider the product of these. We multiply two vectors and we obtain a number. So this is a different thing. P2, Q2 plus P3, Q3. Observe that this is a number. Okay? We multiply two vectors. Instead of multiply, let me say dot product. We dot product two vectors to obtain a number. We don't obtain a vector. Okay, so this number has a geometric meaning to it. Applying cosine rule last time, we showed that let's call this a fact that we are going to use. P dot Q, this number, is equal to the length of P times the length of Q times the angle between them, cosine of the angle between them. Okay, so here recall that P is equal to, okay, let me write square here. It's easier to write it that way. P1 square plus P2 square plus P3 square, and theta is the smaller angle between P and Q. P and Q at the origin. Okay, so remember all vectors are considered starting from the origin. So at the origin, you consider these two rays, and there are two angles, the inside angle that we have in our mind and the outside angle. Okay, the inside angle, so it's not easy to define what inside and what outside is. It depends on where you stand, but there are two angles. The smaller one with the cosine comes here. Okay, so this is this is how we see this, and the picture is something like this. So this is P, this is Q, the vector Q. The length of this side is length of P, the length of this side is length of Q, and this angle is the one that we are talking about. There is this large angle. This is the large angle, which we will not look at. Okay. So this tells us that we can recover a geometric property here, which we cannot, given two vectors, it's difficult to calculate the angle between them. But you see this number, and this number are immediately calculable. You just multiply these corresponding numbers, you obtain a number. Okay, so this gives cosine theta equals P dot Q over the length. Okay, so in particular, we are interested in when theta is pi over 2, because that's, in most cases, that's what we will use. We will look at equations of planes, lines, etc., and these are easily determined when you know something perpendicular to that object. Okay, so in particular, when P is perpendicular to Q, okay, so we say orthogonal. We have to learn this terminology because in some books it's called perpendicular, in most books it's called orthogonal. Okay, then theta is pi over 2 and cosine theta is 0. This forces P dot Q equals 0. Okay, so this is a way to recognize when two vectors are perpendicular. Okay, so this is how we recognize if two vectors are perpendicular. Okay, so this is again another fact which we will use. P is perpendicular to Q means the same thing as P dot Q equals 0. Okay? So the advantage of doing such calculations is that you see this is something that you have to decide by looking at these vectors, and if it is, maybe it is 91 degrees, maybe it's 82 degrees. Okay, you can make an error here, but here you just multiply numbers and add them. If it is 0, they are perpendicular. Okay, so this is called the algebra of these things. That's why you do algebra. Okay, algebra is a tool. It tells you precisely what something is happening, if, of course, you use correctly. Okay, so this is what we did about dot product. Okay, then, so next, we started considering triple products, cross product. Next, we started cross product. Okay, so for this we need to review. We needed to review some determinants. But fortunately, we need only 2 by 2 of 2 by 2 or 3 by 3 matrices. Okay, the determinant of a 2 by 2 matrix, if these are numbers, is AD minus BC. Okay, and here what we want to remember is that it is easy to see here that this determinant is 0 if and only if A, B is a constant multiple of C, D, where for some lambda. Okay, so you can see this here. Okay, so for example, if AB is equal to CD, then you see this is AB minus BA, so it is 0. If there is a constant here, the constant comes out, so it doesn't matter. The geometric meaning of this is that you are calculating the area of the parallelogram formed by this vector and this vector. Of course, if these vectors are the same, they don't form a parallelogram, so you get 0. Okay, so now we have something similar with the with the 3 by 3 matrices. So let me make a remark here. Okay, so this determinant is the area, well, this absolute value of the determinant, because if I change the places of this, we know that we get negative of the previous number. So the absolute value of the determinant is the area of the parallelogram formed by AB and CD. Okay, so maybe I just squeeze it here. Okay, so this is the vector AB. This is the vector, okay, we can go up to here. This is the vector CD. Then consider this parallelogram. Okay, so this area is absolute value of this determinant. It is always useful to keep in mind such geometric information. It's not superfluous because it gives you an idea about what to expect in the next stage. Now, if we know that we are getting the area here, then this is not magic, okay? If one of them is a multiple of the other, then they are all pointing in the same direction. There is no area here, or maybe this is pointing in this direction. So this vector and this vector don't give you any area, so you expect to get 0. Okay, now what about 3 by 3 matrices? Okay, so the determinant, or absolute value determinant of a 3 by 3 matrix gives the volume of the parallelepiped formed by the row vectors. By the row vectors in R3. Okay, so again, if we have this in mind, then you can see that if one of these, you have one vector, and then the other vector gives you a plane. If the third vector also lies in this plane, then you don't get any volume. Okay, so the third vector must be independent of these things. So in particular, if the two rows are the same, okay, you don't get a volume. The determinant will be 0. There are, of course, algebraic ways of proving that if one vector is a linear combination of the other rows, then the determinant is 0, but we are not going into those proofs. We just want to remember this geometric property. And how do we calculate the determinant? Again, let me use this notation. Maybe I used last time. A, B, C, D, E, F, G, H, K. Okay? So, well, we all know from high school that there's a quick way of calculating this. But for our purposes, we want to use what is called the Lagrange expansion of this determinant with respect to the first row. You can do this with respect to the other rows. You can do this with respect to columns. But in our particular application of cross product, we will use expansion with respect to the first row. So this is A times the determinant of, okay, you cover these things. Here you have E, F, H, K, and minus B times, this time you cover these things. You have D, F, G, K, okay, plus C times, this time D, E, G, H. Okay, and we know how to expand these things. So this is what we are going to use. This is the expansion with respect to the first row. Okay, now for for cross product, we will use the following notation. For cross product, recall that we have the vector I, okay, I'm not putting arrow now here, is 1, 0, 0. J is 0, 1, 0. And K is 0, 0, 1. So these are standard directional vectors. And for example, if we have a vector A, B, C, we will write this as AI plus BJ plus CK. Okay, so most of the time this notation is used, but if you get involved in algebra and geometry, then you use this notation, because this notation is easy to expand to higher dimensions. This notation is only for 3 dimensions, but then cross product is only for 3 dimensions. Okay, so now we take this equation, we take the above determinant expression and replace A, B, C by I, J, K on the right-hand side. Okay, so we get I, J, K, D, E, F, G, H, K. This determinant we write. Okay, I'm just now doing this formally. Okay, because you see, as I mentioned last time, when you talk about the determinant of this matrix, it doesn't make sense because we have numbers here and then we put vectors here. Okay, so you can put a bus here, you can put a chair here. It doesn't make sense. But we are saying that this thing will be defined as the following. Okay, so this time, if I replace this by vectors, then it makes sense because I have a vector times a number. That's well defined. And I subtract a vector from the other, I add another vector. So the right-hand side makes sense. So this notation, generally in mathematical books, means that I will use this symbol to mean this. And you'd better write something that makes sense on the right-hand side. So this part, I'll write E, F, H, K, I minus D, F, G, K, J plus D, E, G, H, K. Okay, so now we have on the right-hand side, we have a vector. Okay, so this vector is called the cross product of the vectors that I see here. Okay, so this vector and this vector. So now let me write that. Okay, so this vector on the right-hand side, okay, so this notation is short for right-hand side, is given a name. It is the cross product of the vectors. Okay, let's call them P. It is D, E, F. And Q, and that's G, H, K. Okay, it is denoted notation is P cross Q. Okay, so note that this is a vector cross product takes two vectors in R3 and gives another vector in R3. Okay, so I keep emphasizing R3 because this cross product is, this definition you see is valid only in R3. Okay, in higher dimensions you have to invent something else. Okay, so from properties of matrices, we see that if we change the places of these two rows, the sign changes by -1. So P cross Q is not the same as Q cross P, but it's not very different. You just multiply one by -1 to obtain the other. Okay, so first properties. Okay, maybe let's say just first property, because the others I'll explain. First property is that P cross Q is -1 times Q cross P. Okay, so why do we obtain such a vector? What does it give us? So it again follows from this property. If instead of A, B, C, I write D, E, F, for example, then in this matrix I'll have two rows the same. So the result will be 0. Okay, but what does it mean to put here instead of A, B, C if I put some number? So I come back here, instead of I, J, K, I put D, E, F. Okay, so when you look at this side, it is the dot product of P cross Q with one of these vectors. Okay, so let's make that a general fact. Let P, Q, R be another vector. So let's say R1, R2, R3. Okay, so let's multiply this with the P cross Q, R dot product P cross Q. Okay, so let's see, let me write this properly. R1I plus R2J plus R3K. This is my vector. I'm dot producting it with this thing. So this is something. Okay, let's call this. I don't want to write all of this, so let's call this UV. Or maybe, okay, so let's not change this. So we calculated these things and they turned out to be UI plus VJ plus WK. Okay, so, so when you multiply these things, you will have R1U plus R2V plus R3K. Okay, now I want to write this. That is, this is R1 times EFHK minus R2 times V is DFGK. Well, this K is different than this K, so remember that these are vectors. Well, not this one. These are vectors, but this K is not. Okay, so, and this one is DEGH. Okay, so now you see everything here is a number. When you have this expansion, this is the determinant of the matrix R1, R2, R3, and DEF, GHK. Okay, so now by looking at this thing, we can say something about this. We have this thing on this side, and here I have this determinant. They are the same. So if this vector, instead of R1, R2, R3, if I write DEF here, I know that I'll get 0. Or instead of this, if I write this, I'll get 0 because then 2 rows will be repeating. Okay, so but when this thing is 0, it means that this vector is perpendicular to this vector. Okay, so when I put P or Q here, I get 0 trivially from this expression. So this tells me that this product automatically gave me a vector which is perpendicular to the plane generated by P and Q. Okay, so you have two vectors like this. P cross Q, if this is P, then you always use the right-hand side. From P to Q, your thumb points the direction of P cross Q. So P cross Q is perpendicular to this vector and to this vector. So any vector in their plane, which is a linear combination of these, is perpendicular to P cross Q. Okay, so that is the conclusion. R1, R2, R3 equals, let's say, DEF, F, or the other row, GHK, then the then the determinant is 0 since two rows are the same in the matrix. Are the same in the matrix. Okay, so this is the algebraic result. Now we are interested in the geometric conclusion of this. Geometrically, this means that P cross Q is perpendicular to both P and Q. Okay. Also, any vector in the plane defined by P and Q is of the form C1 P plus C2 Q for some numbers C1 and C2. Okay. So if I take P cross Q, so P cross Q, so this is my vector. If I take dot product of this with C1 P plus C2 Q, okay, we know that dot product distributes, constants come out. We will have, okay, let's write this patiently. P cross Q dot P plus C2 P cross Q. So maybe I also put parentheses here to make life easier. Okay, so this is 0, this is 0, this is 0. Okay, so therefore this is 0. Okay, so again, algebraically we multiply things, we get sum of two zeros. Geometrically, this means, so this is the part that we are going to use when we write equations of lines and planes. P cross Q is, okay, now we use the technical term, orthogonal to the plane defined by P and Q. Okay, so we know that 3 points always define a plane. Okay, here P and Q give you 2 points at their tips, but all vectors start from the origin, so origin is always a point. So you have the 0, P, and Q. These 3 points determine a plane. You take P cross Q or Q cross P. One of them points this way, the other one points this way. That is a vector perpendicular to this plane. Okay. So, of course, the nice things about these things is geometrically, when you try to figure out which line is perpendicular to which plane, if you try to do this visually by hand, it is difficult, but these considerations tells you that a simple calculation gives you a vector. Okay? Taking determinant of a 3 by 3 matrix when the numbers are reasonable, as they will be in the exam, is easy. Okay, so let's see what other properties of this. Okay, one nice property is the following. When you take 3 vectors and you take their cross product, okay, so let's say beware, cross product is not associative. So what does that mean? Okay, so this means that is A cross B cross C, if we have vectors, or maybe since I use PQR, let me use PQR. So P cross Q cross R does not have a meaning. Meaning unless you put in parentheses. Okay, so for example, P cross Q cross R. Okay, so let's see what this is. Okay, so let's say this is Q and say this is R. Okay, so we are going in this direction to do the right-hand rule. So assume that maybe this is Q cross R. Okay, so it is perpendicular both to this one and to this one. It is perpendicular. So now let's take another vector, P. Okay, so P will be, okay, maybe let's take P somewhere here like this. So this is P. Now it is in this direction. Okay, so when you are going this way, it will go the other way. So okay, let me take it on this side so that I can, well, okay, let's continue with this. Okay, so if I do this like this from P to Q, it points the other direction. So it will be something like this. So this is P cross Q cross R. Okay, it is this vector. This vector is perpendicular to this, but in particular it is perpendicular to this. Okay, so this is perpendicular to Q cross R. Okay, so it is not important that it is perpendicular to P in our case. Okay, we are in R3. We have a vector perpendicular to this one, but this vector is also perpendicular to this one, and this vector is perpendicular to this one. So these three vectors are in the same plane. Okay, so conclusion. P, Q, and R lie in the same plane. Why? Because since they are all perpendicular to Q cross R. To the same vector, let me say, to the same vector Q cross R. Okay. So, conclusion from this, therefore, from this conclusion, we have the following. There is some number times Q plus some other number times R for some numbers C1, C2. Okay. Obviously, if you now do this, if you put parentheses here, it will be in a different plane, not in this plane. So these numbers, you don't expect them to be the same vector. They will be all lying in different planes maybe perpendicular to each other. And in fact, we can determine what these numbers are. We can determine what these numbers are, what C1 and C2 are. So if I'm not mistaken, check this from this book. I'm just now lying. This must be P dot R, and C2 is minus P dot Q. Okay, so check this, or maybe I check this from here. Okay, so this one is, okay, this one, I think I wrote it correct. Okay, check this from the book. Okay, so how do you prove such a thing? Okay, sometimes there are big theories. You stare at the problem for half an hour, and then you find a proof, which is 2-second proof. But sometimes there are no such big theories. You just write both sides. Okay, so you write the coordinates. You know the coordinates of P, Q, and R. You write this cross product on one side. Okay, and then you see on this side you have dot products times these numbers, these vectors. Okay, you write that on the other side and check that on both sides you get exactly the same thing. So that's how you prove this. Okay, so this is one thing to remember, that cross product is a strange product. Your intuition does not work here. When you change order, the sign changes, and you don't write P times Q times R. it will not make sense if you don't put parentheses. Okay, so that's our thing. And there is one Jacobi identity which you can check in the book. Okay, so such identities are not worth remembering if you are not working with them all the time. So I will not write it on the board. Okay, so maybe we can do some examples. Let's see. Another obvious thing about cross product is maybe when is the cross product 0? Okay, so when will the cross product be 0? Again, cross product is given as a determinant. Okay, in the first row you have I, j, k, and then you have two vectors here. So you write this out. Okay, so this thing will be 0 if the determinant will be 0 in our case if two rows repeat or one row is a multiple of the other row. This ijk is not going to be multiple of any row because it's a row consisting of vectors, so it's a formal row. Okay, so it doesn't enter into these considerations. You have the other two rows, they are given as numbers. If one of them is a constant multiple of the other, then the general determinant rule tells you that you'll get 0. Okay, so this is algebra. Geometrically, what does it mean? It means that this vector and this vector are along the same line. Either they are pointing in the same direction or in exactly the opposite direction. Instead of saying this whole sentence that they either go in the same direction or in opposite direction, one of them is a bit larger than the other, we just say they are parallel. Okay? If two vectors are parallel, then their cross product is 0. Here the word just parallel is a summary of this explanation, that they either point in the same direction, one of them maybe is larger than the other, or they are pointing in opposite direction. So let me make a note of that because that is, again, something we use. Of course, if two vectors are parallel, it is not difficult to see them. They are parallel even when their coordinates are given. But this time, this is used when you get a cross product at some place and it is 0, then you know that the vectors were parallel. Okay? So another property. So P cross Q is 0 if and only if. So it's the same thing as P and Q are parallel. Okay, so this means parallel means P is equal to lambda times Q for some number lambda. Okay, if lambda is positive, they are pointing in the same direction. If lambda is larger or smaller than 1, then you compare their sizes. Okay, so this is because P cross Q is I, J, K. These are vectors. And here you have P1, P2, P3, Q1, Q2, Q3. Okay, so I'm here, I mean the determinant, so let me write determinants here. Okay, so if one of these rows is a multiple of the other, the determinant is 0. Okay, so that's what we know from fundamental determinant properties. Okay, so this is another thing to keep in mind. If P dot Q is 0, they are perpendicular. If P cross Q is 0, they are parallel. Okay, so that's the last maybe fact we want to write. So summary, P dot Q equals 0, they are parallel. They are perpendicular. P cross Q equals 0, they are parallel. Okay, so this is the geometric thing, when the geometric conclusion when these products are 0. And this is a vector, okay, so maybe we also add that. P cross Q is perpendicular to P and also Q. Okay? So after all of these conclusions, the idea that we have to keep in mind is this. Of course, throughout this course, you have to remember the definition of dot product, cross product. Okay, that saves you time. But after the course is over, when in real life you are using, when you need these things, the thing that you should remember from calculus is whether a problem you face in life is related to calculus or not. Okay, so that's education. You don't have to remember these formulas. You don't have to remember how these theorems are proved. Nothing of the sort. Education is that when you meet some problem in life, in your profession, you have to determine whether this can be, which part of this can be solved with calculus, which part of this can be solved with some other branches, okay? So that you ask experts, the correct experts to solve it, or you go to the correct books to check how these things are done, okay? But until you pass this course, of course, you have to memorize a few formulas. The reason to memorize these formulas is because it saves you time in the exams. Okay? Of course, you can always derive these formulas, or maybe some formulas will be given to you. But if you know these formulas by heart in the exam, you don't waste time trying to understand what the formula given in the back of the exam is, or whether it was plus or minus at a crucial point. Okay? So memorization saves you time in the exams, but after that, just remember what is related to what. Okay, so maybe I do finally some numerically. Okay, properties of cross product. I'll leave it to you to check in the book. It's easy. Okay, so after all these theoretical things, you see that I didn't write any number. The only numbers I wrote are indices 1, 2, 3. So let us put some numbers somewhere and calculate a few things to see that these things really work. Okay, so let's start with the trivial thing. Let's take two vectors. Let's take their dot product and cross product. And then in one of these vectors, we'll put a variable, and we'll check if we can make this variable to see if these vectors are perpendicular or parallel. Okay, so let's invent a problem like this. Okay, so let P be 1, 2, 3, and Q will be, okay, so minus 2, 0. Let's make life easy. Let's make one of them 0, and this one 4. Okay. Well, let's make this something even. Let's make this 1. Okay, so we have these two vectors. Okay, so we calculate P dot Q. Okay, 1 times minus 2 plus 2 times 0 plus 3 times 1. Okay, so minus 2, 3, 1. Okay, so this is the, of course, now put any numbers there, you'll get a cross product, you'll get a dot product. Let's look at P cross Q. So this is the, okay, so sometimes I write determinant here, sometimes I don't. Sometimes this sign means that we are calculating the determinant of the matrix, but in some books this sign is used as denoting the parentheses of the matrix. So, okay, so let's use both of them. Determinant of this, I, J, K. I write this 1, 2, 3, minus 2, 0, 1. Let's see what happens. Okay, so the first entry is this determinant, 2 times 1 minus 0, so this is 2. And the second entry is minus this determinant. This is 1 plus 6, 7, so this is minus 7. Okay, and the last one is this plus 4. Okay, and sometimes I think in the exams you will always see it like this. Okay, so when you are especially working in R3, some people prefer to use this notation. Okay, but I'm myself a geometer. I work in n dimensions, so I always use this one. But it's a personal taste. Both of them are correct. Okay, let's check Q cross P. Observe that here it doesn't make, since this is just multiplication, this is the same thing as Q dot P. Okay, so if we did the calculations correctly, this should be minus that vector. Let's check if we did this correctly. So this time I take minus 2, 0, 1, 1, 2, 3. Okay, so the first one is, you see, minus 2. Okay, so far so good. So the second one is I take minus this one. So minus 6, minus 1, minus 7, plus 7. And the last one is this thing, minus 4. Okay, so the numbers turned out to be correct as we were expecting. So notice that this is now minus P cross Q. Okay, so I want to put a number here. Instead of 0, let us put x there. And let's find out, let's see, okay, we have time. Let's find out if we can choose x so that P will be perpendicular to Q. Okay, so let's do that here. P to be again 1, 2, 3. Q this time is going to be minus 2 x 1 for some parameter x. Okay, so find x such that P is perpendicular to Q. Okay, so that's the problem that we invent. Okay, so obviously you see that trying to do this in R3 visually is not feasible. We use algebra here. We take the dot product of P and Q and check if we can solve for x so that the dot product will be 0. Okay, so solution. Of course, this is a simple problem, but I'm trying to just give you the essential of a complicated problem. The real problem may have lots of other stories, but you should see through it, and you should recognize that at some point you have to get the dot product of two things and decide if it is 0 or not. Okay, so P is going to be perpendicular to Q when P dot Q equals 0. So we calculate P dot Q as, okay, so 1 times 2 is minus 2, 2 times x plus 3. Okay, so we just calculate this one. So this is equal to 1 plus 2x. We force it to be equal to 0. We force this. We force it to be 0. Now, fortunately, x can be solved. Okay? Is there a case when x cannot be solved? If corresponding to this, instead of 2, we had 0, then the dot product will not have x in it. The dot product is fixed. So no matter which x you choose, the dot product will be that number. And if that number is not 0, you'll never make them perpendicular to each other. In this case, corresponding number is non-zero, so x appeared here. So this gives x equals minus 1 over 2. Okay, so most students will leave it like this. This is not a solution. This is a calculus solution. Okay, so this is the problem. Okay, so this is the problem. Now x equals minus 2 you have to answer this question. Okay, so the answer, when x equals minus 1 over 2, P is perpendicular to Q. Okay, so let's stop here. Next hour, we'll apply these to lines, planes, and curves. Okay, any questions? Peki.